We start for this week subsurface water part 2, which is green Ampt equation and ponding time equations. Green Ampt equation is, we know that so far infiltration equation were derived from approximate solution of Richards equation, but right now for the green Ampt equation, Green and Ampt propose an alternative approach to obtain more approximate physical theory with an exact analytical solution. So we obey more exact solution with using analytical method. Okay. They thought, and as schematically expressed, shown, the wetting front is sharply divided after length of depth, this wetted zone. Okay, in this schematic view, H0 is ponding height, which is above the surface, whatever the water is, there is just water layer. All right, the L is the wetting front penetration rate depth, which is the water goes inside this ground to do that. This length of this L length of depth moisture zone. Okay, theta R on the one layer, which is, this is residual moisture, which means if we dry out all this soil, the residual amount of moisture is gonna stuck there. This is very small portion of the soil, so it's called residual moisture. And theta I is soil moisture content, which is each moisture, each soil has their own characteristic and moisture content. Theta E is effective porosity or effective moisture, let's say effective moisture, which is when we subtract the porosity, which is eta, porosity minus residual of moisture. That means that this amount of this effective moisture, this what's that? This amount of moisture, it can be taken by the soil. This is the effective or the potential of moisture content. Okay, let's remember again our Reynolds transport theorem again, and how we are gonna start. We are gonna start again with the continuity equation. Let's take a column of cylindrical soil column. Okay, and we said that there is an, as you see, the gray shaded area is start with the ground surface, then till the wetting front. The top H0 level is ponding of water layer. Okay, then this gray shaded area is wet soil from ground surface, between ground surface to wetting front, and later on, after wetting front, we will have dry soil, which is the water started to infiltrate. It will try to go till the moist, this dry soil. Okay, this continuity equation, if we take it into account, we have cumulative infiltration FD is equal to the length of this ground surface, between ground surface and wetting front, the length of this L multiplied by delta theta, which is porosity minus the soil moisture, right? Porosity minus soil moisture is gonna give us delta theta. This means that there is that much amount of water can go inside the soil, because we already have this moisture content delta E, and we have porosity, the air content. So we want to cover this air with water. That means if we saturated this wet soil fully saturated, we can have infiltration rate, cumulative infiltration of L delta theta. Okay, let's jump to momentum equation. We know that from Darcy's law, Darcy flux is equal to minus hydraulic conductivity, the first derivative of head loss, total head loss with respect to the elevation. Darcy flux Q is constant throughout the depth, as you remember last lecture. And think about it's going upward. Right now the infiltration is downward. That's why it can be equal to, we can consider Q as minus F. If we plug instead of Q minus F, we are gonna have F is equal to K, which is hydraulic conductivity. Infiltration rate is equal to hydraulic conductivity, which is delta H over del Z, del H over del Z. We can open form, which is delta H over delta Z, which is H1 minus H2 and Z1 minus Z2, which is the elevation over change of head loss. The head H1 is equal to ponding depth H0, which is the like the ponding depth, the water surface depth, okay, on the water depth on the surface, and the head H2 is equal to suction head minus the depth, which is the gravity, right? So therefore, if we substitute all these terms, it's gonna be F is equal to hydraulic conductivity H0 minus suction head minus the depth of infiltration over depth of the infiltration again, from ground to wetting front, which is equal to K suction head plus L over L, which is, we can say the ponding depth is very small and it can be negligible. Alright, after we find the infiltration rate, let's remember again the continuity equation. It was L is equal to, or the infiltration, cumulative infiltration is the length, the depth multiplied delta theta, okay, the potential moisture content. When we apply for L is equal to F over delta theta, we are gonna end up the infiltration rate is equal to K psi delta theta plus cumulative infiltration over cumulative infiltration. We know that the infiltration rate is the first derivative of cumulative infiltration with respect to time. Then we can write it, this above infiltration rate equation, as an differential equation, which is dF over dt is equal to K psi delta theta plus F over F. So it is a first order nonlinear ordinary differential equation. I just jumped to the result. I didn't want to go through detail how we are gonna solve. If you want to know, you can ask me, or you can go through from your calculus knowledge. Okay. This first order nonlinear ordinary differential equation result gives us the infiltration rate is equal to KT plus psi delta theta natural logarithm of 1 plus infiltration, cumulative infiltration over suction delta theta. So this cumulative infiltration can be obtained by trial and error iteration method, because on the left hand side and the right hand side there is an F. So we just gonna give on the right hand side whatever the value is, like we are gonna give maybe like KT at the beginning, okay? And we just apply this number, then we will compare on the left hand side. If it is different, whatever you get on the left hand side, you are gonna plug on the right hand side till right hand side FT and left hand side FT is gonna be equal. Then we will obtain the solution. This is called trial and error iteration method. Before we go any further, we need to know the green Ampt parameters. Application of green Ampt model requires estimates of the hydraulic conductivity, which is represented by K, capital K, the porosity, which is represented by eta, and the wetting front soil suction head, which is psi. Okay, the variation of moisture content theta affects suction head and hydraulic conductivity. This is studied and proposed, observed. Okay, and it's found that suction head can be expressed by effective saturation SE, which is given the equation F of SE is equal to theta moisture content minus residual moisture content over porosity minus residual moisture content. And the relationship between moisture content and effective saturation can be written as we know that delta theta is porosity minus initial moisture content is equal to 1 minus SE effective saturation, 1 minus effective saturation multiplied by effective moisture content. Here is very useful soil type of green Ampt infiltration parameter for various soil classes. We have sand, loamy sand, sandy loam, silt loam, sandy clay loam, silty clay loam, sandy clay, silty clay, and clay. All this porosity, effective porosity, wetting flow, soil suction head, and hydraulic conductivity is given on this table. If we ask any question, we just need to look this table, and then we are gonna bring up we will solve our question. Okay, before we jump to any example to solve, let's go through again green Ampt model. But if we have two layers, because we know that soil is constructed by layers. One layer maybe consists of clay, the other one consists of silt. So it's layer by layer. That's why we need to apply multiple layer of green Ampt model. On the right hand side, you see there is an upper layer parameter and lower layer. Okay, and we have wetting front. Then after that, we have the bottom side of H2 for this lower layer. In lower layer, there is like two different categories too. Again, in the upper layer of wetting front, we know that is like it has wet layer. The bottom of below of wetting front is dry layer, right? If we have this kind of example, we need to apply for the infiltration rate K1 K2 H1 K2 plus L2 K1, which is suction F2 plus H1, which is the depth of the first upper layer and the length of the second layer before the wetting front. All right. And for the cumulative infiltration, which is H1, which is the upper layer, delta theta 1 plus L2 delta theta 2. Why we are taking L2? Because we know that after L2 is a dry soil. That's why we don't count this H2 minus L2. And when we substitute, combine all these two equations, we are gonna end up the two-layer green Ampt equation, which is L2 delta theta 2 over K2 plus 1 over K1 K2 delta theta 2 H1 K2 minus delta T2 K1 suction F2 plus H1, and natural logarithm of 1 plus L2 over suction 2 plus H1, which is equal to time. It's just like we are taking time and then we solve this equation. All right. Like this, just like for your knowledge, you don't memorize this one. I'm just giving you, if you need it in your future research, you can use this one for 2 layer, 3 layer, 4 layer. All right. So you just need to simply adding the layers inside the continuity and momentum equation. We are going to compute the infiltration rate F and cumulative infiltration capital F after 1 hour of infiltration into a silt loam soil that initially had an effective saturation of 30%. Assume water is ponded to a small but negligible depth on the surface. We are going to go back to our presentation, and then we will use this table, which is green Ampt infiltration parameters for various soil classes, and we need to concentrate on silt loam. As you see, the porosity is 0.501, effective porosity is 0.486, and wetting front soil suction head is 16.68, and hydraulic conductivity is 0.65 centimeter per hour. We are going to use these parameters and we are going to solve our question. Alright, let's start to solve our question. We know that we have 1 hour, right? Let's see. Let me take this guy here. Let me here. Okay. So it's 1 hour duration into a silt loam soil, and our saturation, effective saturation is 30%, which is denoted by 0.3. And what we need to find is, let's put again here, we need to find infiltration rate and cumulative infiltration. We need to find it. From the table, we know that, let's plug here, we know that our effective moisture content 0.486, and our suction head is 16.68 centimeters. Hydraulic conductivity is 0.65 centimeter per hour, and porosity 0.501 for where is it? For silt loam soil. All right. So after we know this one, what we need to use? We need to use green Ampt equation, which is here. I wrote here is the cumulative infiltration is equal to hydraulic conductivity multiplied by time duration plus suction rate multiplied by changing of moisture content of soil, and natural logarithm of 1 plus cumulative infiltration over the phi multiplied by delta theta is gonna be our green Ampt equation, right? So we need to continue. We need to apply all these terms what we know from here, k, phi, and we know that time is 1 hour. Then we just need to plug, and just because it is nonlinear, we need to use iteration. Then we will find what is ft. All right. First of all, but we need to know what is delta t. It is not given by the table, right? we have a formula of delta T, which is we set green Ampt parameters. Let's just remember delta T is equal to 1 minus effective saturation parenthesis and effective moisture content, which is 0.486 for silk loam. After we know all this, we are gonna pass by to apply all these parameters to green Ampt equation in order to find cumulative infiltration first. Okay, first let's plug our delta T term and then find what is delta T in numerical form. Okay, what was delta T? It was 1 minus effective saturation, which is 0.3, 30%, multiplied by effective moisture content, which was 0.486 from table. And when we multiply each other, we will find 0.3402. This is our change of moisture content. Okay. After that, we just need to apply, we need to plug all these terms in our green Ampt equation, and it's gonna be make it straight, yes. Cumulative infiltration is equal to suction head, which is 0.65 multiplied by 1 hour plus suction head, which is 16.68 multiplied by delta theta, which we found here, this 0.34.02, and we need to multiply natural logarithm of 1 plus cumulative infiltration 16 point sorry 6.68 sorry 16.68 multiplied 0.3402 is gonna be our green Ampt equation. What we need to do, we need to give one number to here, and then we need to check if it's fit. It's gonna be the same answer. So it's an iterative procedure. In order to do this one, I start with a give cumulative infiltration KT, which is 0.65. I will just give 0.65 and then I will check what is gonna be for FT here. Let me, okay, let's give, hold on, let me choose this guy. Okay, let's give 0.65 for cumulative infiltration on the right hand side, and then let's plug it for our green Ampt equation, which is gonna be our second like final cumulative cumulative infiltration is equal to 0.65, which is our KT plus 5.67, which is multiplication of 5 delta T and natural logarithm of 1 plus this FT cumulative infiltration. I just give 0.65 and I'm gonna check what is gonna give for later on, what is gonna give for FT. So first infiltration, I get one point. So if when I put here 0.65, I get F 1.265. Then after that I apply again, I plug 1.265 for F on the right hand side over here. Then after that I will calculate again. I calculate again the cumulative rate, and at the end I found it this one. So after I put 1.265, I found that 1.792 cumulative rate on the left hand side. Then after that I plug again and then again and again, iterative function. When I put 3.167 on the right hand side here 3.167, I found the same similar results on the left hand side. So I said, okay, then I found the cumulative rate for this solution. Then I make my solution. Cumulative rate is 3.167 centimeter of water. Okay. Then after that, I need to find infiltration rate. The question was asking me find infiltration rate, which is F is equal to hydraulic conductivity multiplied by suction head multiplied delta theta over our cumulative infiltration plus 1. I know cumulative hydraulic conductivity, suction head, delta theta, cumulative infiltration, and right now I just need to plug it all these terms, and I found that my infiltration rate is 1.81 centimeter per hour. So new subsection is ponding time. We need to previously we just concentrate on infiltration, cumulative infiltration and infiltration rate, but we didn't count on ponding, ponding on the surface. In the green Ampt equation, the infiltration rate and cumulative infiltration are related by F is equal to K psi delta theta over F plus 1, right? Under constant rainfall intensity, F is equal to I. We are saying the ponding of infiltration is ITP. It means like whatever rain comes, whatever the intensity, if you multiply by the ponding time, is gonna infiltrate into the soil. As you see on the right hand side of the graphically shown. Okay, it goes linearly first, then after that infiltration is start to decrease by time. And ponding time, how we are gonna calculate ponding time is hydraulic conductivity multiply psi delta theta over intensity of rain multiplied by intensity of rain minus hydraulic conductivity. In this example, compute the ponding time and the depth of water infiltrated at ponding for a silt loam. Again, the same soil type. Again, 30% of initial effective saturation, subject to rainfall intensity of A, 1 centimeter per hour, B, 5 centimeter per hour. Two different cases. We are gonna solve from, we can get help from our previous example, and we will solve this question. In this question, we are gonna find the cumulative infiltration for ponding and ponding time. Let's write it down here. For intensity of rainfall, intensity of 1 centimeter per hour and 5 centimeter per hour. So we are gonna compare, then after that we are gonna compare what's going on. While we are using this, while we are finding this question, we will use the previous example, silt loam. Remember that we have suction head multiplied delta theta is 5.67 centimeter and hydraulic conductivity was 0.65 centimeter per hour. Ponding time, when we apply these parameters into ponding time equation, which is hydraulic conductivity multiplied by delta theta over intensity of rainfall multiplied by intensity of rainfall minus hydraulic conductivity. For first one, let's try first intensity of 1 centimeter. Let's put here. Then let's draw here one. These guys, okay, for 1 centimeter per hour. And when we apply 1 centimeter per hour, then we just need to plug all the parameters here, and which is right. So when we apply 1 centimeter per hour intensity of rainfall, we just need to apply this hydraulic conductivity 0.65 multiplied by 567, which is 5 delta theta over 1 minus 0.65, which is 10.53 hours. So that means in order to pump the water over surface, it needs 10.5 hours in 1 centimeter hour intensity of rain. And during this 10 hours, how much water is infiltrate? Let's calculate this one because it's constant. So if it is constant, we just need to multiply ITP, which is ponding time multiplied by intensity. This is all whatever the rain comes is gonna infiltrate into the soil, so we just need to multiply it. So 1, which is I, multiplied by ponding time, which is 10.53, which we found here in this equation. So it's gonna be 10.53 centimeter of water infiltrate to the soil. Okay, let's go to 5. If we have 5 centimeter, so at, let's say here, I is equal to 5 centimeter per hour. Again, we need to apply our ponding time equation. When we apply ponding time equation, we are gonna see 0.65, 567, 5 parenthesis 5 minus 0.65 hydraulic conductivity. And here you can see, let's see if I can. Here 0.69 hour, which is around 0.2 hour, which is 10 minutes, right? So 10 minutes of duration if our rain is 5 centimeter, which is 50 millimeters per hour intensity. If it has in 10 millimeter, the water start to gather on the surface very fast. It was 10 hours, right now 10 minutes. If in 10 minutes, then how much water infiltrate in the soil? So we are gonna calculate it. What we need to do, we need to multiply ITP. I was 5. We need to multiply by 0.169. It is given us 0.847 centimeter, which is almost 1 centimeter of water infiltrate into the soil, which gives us an idea that if the intensity of rain is low, like 1 centimeter, it's gonna take too much time to pond the water, and we will take all the water inside during this time. It's gonna take all the water inside the soil. But if it takes 5 centimeter per hour, which is the intensity is high, then it start to occur in 10 minutes. Then of course, if you take relatively this number here, the number is high, but in civil engineering point of view, we don't want a high intensity of water rainfall, because it start to pond the water. Let's say we have a surface, and then it start to get higher and higher on the surface, which is start to have flooding, and that's why we are taking the drainage to go inside the water in this drainage and then take away from our streets. But if the intensity is high, it start to accumulate very straight, like very fast, and it's gonna be hard to design to get rid of this problem. All right, so in this question we are done here, and let's go. If the ponding stop, like ponding time, if we have a rain intensity over, like after ponding, what will happen, how much water we are gonna infiltrate into the soil. We found that how much infiltrate when the ponding, or like when the till the ponding occurs. Okay, right now we are gonna find after ponding occurs, like let's say in like 10 minutes or 15 minutes or 50 minutes. After 50 minutes, 2-hour period, what's gonna happen? How much water infiltrate into the soil? Okay, so for T bigger than TP, it means the time is bigger than ponding time. What are we gonna do? First, we know that the ponding FP, we can write it into the ponding time equation. Okay, for green Ampt equation, which is FP is minus suction at delta theta ln 1 plus FP over suction at delta theta is equal to K TP minus D0, which is giving us the ponding infiltration. When T bigger than TP, we know that we can write it F minus suction F suction at delta theta ln 1 plus cumulative infiltration delta pi delta theta is equal to K T, which is total T minus T0, beginning of the rain. So when we add, like subtract each other, we are gonna find the F minus FP minus suction at delta theta ln suction at delta theta plus cumulative infiltration suction at delta theta plus ponding infiltration is equal to hydraulic conductivity T minus ponding time. Total time minus ponding time. When we subtract each other, we are gonna find the infiltration occurs into the soil when it is bigger than ponding time. Okay, when the time is longer than ponding time. Let's go through an example. We are gonna see. We are gonna calculate the cumulative infiltration and the infiltration rate after 1 hour of rainfall of intensity 5 cm per hour on a silt loam soil with an initial effective saturation of 30%. Again, the same example, previous example, but here it's gonna be, instead of ponding time is gonna be extend the time for 1 hour. Let's solve this question. In this question, we are gonna find infiltration rate and cumulative infiltration. Let's plug here our solution. Okay, we are gonna find the infiltration rate and cumulative infiltration at 1 hour period. And here, and again, we are gonna take from previous examples. If we have again silt loam, what we had is delta theta is 5.67, right? And hydraulic conductivity is 0.65. Ponding time for 5 centimeter per hour, which is previous example we calculated, almost 10 minutes, which is 0.169 hours, and cumulative infiltration is 0.847 centimeter for 5 centimeter hour and in 10 minutes. So it says after 10 minutes, like we have 1 hour period, right? Like what happened after 50 minutes, 50 more minutes, rain occurs in like 5 centimeter hour intensity. So we have another formulation, as you remember. It was the cumulative infiltration minus ponding time infiltration and minus suction at delta theta, natural logarithm of suction at delta theta plus infiltration, cumulative infiltration over suction at delta theta plus ponding time infiltration is equal to hydraulic conductivity multiplied by total time minus ponding time. So we don't know the cumulative infiltration. We need to calculate the cumulative infiltration. As you see over these two, let's see, let's write it here. Okay, this guy and here this guy, these two is in a non-linear form, and we need to use again iterative procedure. So we are just gonna assume one number like 0.65. Then after that we are gonna make it closer value each other. Like we are gonna make it this iteration all the time till this number is gonna be the same as this number. Okay. So first of all, let's plug all these numbers. Okay. Let's plug these numbers, which is f minus 0.847, which is cumulative ponding infiltration, minus 567 psi delta t, natural logarithm of 5.67 plus f, which is we want to know, over 567 plus 0.847 is equal to 0.65, which is the hydraulic conductivity, parentheses 1 hour minus the ponding time 0.169. After we plug this one and I'm making trial and error, I'm gonna skip this procedure. I made it the first iterative procedure in the first example. You guys end up 3.02 centimeter for f. If you add this one 3.02, you are gonna find 3.02 on the natural logarithm inside as well. Okay. After you find these numbers, what we need to calculate the infiltration rate. The question is asking not just cumulative infiltration, we need to find infiltration rate as well. We know that infiltration rate is the function of cumulative infiltration. We just need to substitute all these numbers. Then we are gonna find here. The infiltration rate is 1.87 centimeter per hour when we substitute all these numbers to the equation. Okay. Here is the important thing. Let's go back here. The cumulative infiltration 3.02 centimeter when the ponding occurs. Okay. Let's go back to the previous example. What we found it. Okay. We found for 1 hour infiltration, where is it? Here, 3.167. So let me copy this one. Let's go back to what we solve right now, which is here. Okay. So as you see here, we found 3.167, but when the ponding occurs, the infiltration in 1 hour 3.02 centimeter, which is almost 0.14, like 1 millimeter, let's say 1 millimeter, 1.4 millimeter less water infiltrate in 5 centimeter per hour in intensity of rainfall. This because in this one, in the first example, we didn't account any infiltration rate, ponding rate. We said all the rain comes and goes inside the soil. That's why we found 3.167. But in the last example, we counted, we calculated the ponding time, because we said if 5 centimeter per hour intensity of rain comes to the soil, it will start to ponding on the top layer. Then after that, it's gonna infiltrate. This cause less infiltration, cumulative infiltration for the soil. All right. So we are done for this question. Before end up our this week class, I will just give you guys a quick review. There's an equation for calculating ponding time and infiltration after ponding occurs. We have 3 different equations: Green-Ampt equation, Horton's equation, and Phillips equation. And in the equation 1, 2, 3, 4, 5, 6, we are having, and for variable calculated, for example, in number 1 is potentially infiltration rate as a function of time. If you want to find in Green-Ampt equation, first of all you need to solve for f from number 2. Then after that you need to use number 6. Then you will find your infiltration rate. So it's giving you a step how you are going to calculate. In Horton's equation, there is a constant rate beginning of f0, and we need to use this f is equal to fc plus f0 minus fc exponential minus kt. And for Phillips equation is f is equal to 1 over 2 sorptivity times square root of 1 over minus 1 over 2 plus hydraulic conductivity. Then if you want to find potential cumulative infiltration as a function of time, you will find all these 3 equations. Then each case is giving you an idea how to solve or use the step. Okay, this is a very basic table you guys can use. We finished this section, subsurface water. We are gonna jump to surface water. I don't give you guys homework. Why? Because we will have midterm. That's why you guys have no homework. you guys need to concentrate on atmospheric water and subsurface water and hydrologic process. And we are gonna have our midterm, then we will continue our surface water, and then we will continue our statistical approach on the hydrology. Take care of yourself and good luck for your exam.